Good morning, everyone. Today I'm very excited to share the topic about AI solutions for predictive maintenance by showcasing use cases from real-world use cases from manufacturing companies that we have been collaborating in different research projects. I'm Ebru Turanoğlu Bekar, currently working as a senior lecturer in the Division of Production Systems in the Department of Industrial and Material Science and at Chalmers University of Technology. So I am also part of the research group under this production system division, which is called Production Services and Smart Maintenance, leading by Professor Anders Skog. So my research focus in building structured data analysis, data structures, analyzing industrial big data set to identify some sort of challenges and putting some data pre-processing approaches, and also developing some smart maintenance algorithms to support data-driven decision-making in the maintenance field. First, let's introduce to this presentation agenda. So I will first start with some overview of predictive maintenance, which is a fundamental maintenance need in this digitalization era. And afterwards, I will continue with this AI-powered predictive maintenance, which AI is driving predictive maintenance to the next level. So I will give some sort of key components of AI solutions for predictive maintenance, but at the same time also giving some sort of what are the machine learning approaches do exist for predictive maintenance, basically in general. And then through with these real-world use cases from manufacturing, I will show power of AI in practice, especially selected 2 use cases from our research projects that we have been collaborating with industrial partners. And the first use case will be focusing on how we can create health index, machine health index, using some different AI algorithms and approach, and in order to monitor the machine health. And also the second use case will be about early fault or air leakage detection in a pneumatic system that we worked in another manufacturing company in this collaborative research project that I will introduce later on. And then, of course, we believe that there are very much benefits of using AI for predictive maintenance, but still we need to consider some sort of practical aspects and challenges when it comes to the real implementation of predictive maintenance. So I will talk about what are those challenges or practical aspects, considerations in implementing predictive maintenance in real world. And then in conclusion, I will finalize my presentation, some sort of highlighting key elements regarding with the successful predictive maintenance implementation in manufacturing. By the way, I think I just forgot. If you would like to get some more information regarding with my projects and my research, please visit this QR code displayed, web page displayed in this QR code. I think there are more information about the projects and our publications together with my colleagues. So I think everyone knows that, but modern industrial systems have become increasingly complex, especially incorporating Industry 4.0 technologies and connected components. It makes it even more challenging. And so companies have been facing growing cost pressure. And at the same time, they need to optimize the maintenance operations in order to improve the efficiency and productivity. So maintenance needs are also evolved in another way in order to compromise this complexity of this industrial system. And of course, some traditional maintenance approaches such as reactive maintenance can be highly costly and inefficient and also, of course, lead to some increased downtime and unplanned repairs. So with this digitalization and advanced tools, advanced technologies that we have, we are able to collect vast amount of data, and we are able to analyze this vast amount of data at the same time. And therefore, there is a shift from traditional approaches to more towards the smart maintenance approaches, which is more proactive maintenance and digitalization-driven maintenance strategies. And in that sense, predictive maintenance has emerged as a solution to address these maintenance needs proactively, especially by leveraging AI and data science in order to escalate, in order to prevent some problems before they occur in the manufacturing. So predictive maintenance, in that sense, is intelligent health monitoring of equipment to avoid future equipment failure through intelligent monitoring. So when we predict the failures in advance, of course, we can do the maintenance planning, and then we can optimize the maintenance process and then other resources as well. So, but the predictive maintenance is not only predicting the feature failures, but at the same time it pinpoints the problems in the complex machinery by identifying also in the complex machinery which parts needs to be fixed, which parts are problematic. Then we need to understand and we need to solve this, or we need to take care with this part and so forth, or components or critical components in the complex machinery. So with the vision of failure-free production, of course, predictive maintenance can help operating more efficiently, more reliable, and of course, it helps to eliminate unplanned downtimes and maximize the equipment lifetime. And at the same time, it can help to more safer production environment, and this can lead to more increased social sustainability in the production, in the shop floor. Since we are able to manage the inventory management and other resources in advance, since we know when the equipment or when the machine breaks down, of course, we also have more increased resource efficiency, and the whole process can help to minimize the cost, and we have more cost effectiveness and more productivity and so forth. These are the expected impact of predictive maintenance. So predictive maintenance helps make maintenance decisions based on the data. And of course, we use the data in order to answer some sort of questions regarding with our machines. And basically, the first question is, in most of the case, also in real world, we generally take care with this application. Just a very simple question: is my machine is operating normally? And in most of the case, this is called anomaly detection. So we do try to understand if there is a deviation if the machine deviates from the normal operation. So we can call it anomaly detection in predictive maintenance terminology. And also the second important question: why, if there is something we observe in some sort of data, start trending in some sort of parameters that we think is important for machine health? And then second question: why is my machine behaving abnormally? So we need to understand, we need to dig into more this information, and then understand which parts are started aggregating or some sort of getting some unhealthy situation. So this is basically called condition monitoring in predictive maintenance terminology. And once we know that which parts we need to fix, there are some sort of degradation patterns in the part and in the components. So we need to know that still I can run the machine, but we need to understand how much longer can I also operate my machine under these conditions. So which we can call it estimating remaining useful life of the critical components and machine. So in summary, when we have this complex large data set from the machines or other data sources, we are able to make some sort of maintenance decisions and actions in advance. As we know that digitalization, of course, give the companies or manufacturing companies basically to use some sort of technologies like artificial intelligence, big data analytics, and IoT technologies. So we are more connected, we are getting more data and collecting and storing more data from the machines. And these technologies actually work together to have the advanced maintenance solutions in manufacturing. But also there are different components that we need to think about when we are designing AI solutions. In most of the AI solutions actually start with understanding first these three key components. And the first component is data, which is including the data collection and pre-processing, which we need to get the relevant data from the machines or other data information systems, machine controller systems, sensors, or some other data systems in the production. And also another important element of this data component is feature engineering. So we need to also understand what features are relevant, what signals are really relevant to use for the modeling phase. And modeling basically covering model selection and design. So we need to understand what type of problem we want to solve, but based on the availability of the data that we have. And then we need to design these models, AI models, machine learning models, basically. So we need to train and tune some sort of these model parameters in order to get good predictions, good predictive analytics in order to forecast the equipment failures. And then another component is decision making, because decision making is important for providing maintenance recommendations. And with the real-time monitoring, we are able to get the data continuously, get the data streams, and also we are able to chance to deploy and maintain the AI algorithm for get up-to-date predictions in real time. But here, the most important component is also the feedback loop, and the feedback loop basically provides the outcomes that we get from the model, maintenance outcomes or decisions are fed back into the model in order to improve AI model and keep it up to date, basically. So these three components are important for AI solution for predictive maintenance. So machine learning is a special branch under artificial intelligence, under AI, that uses some specified learning algorithms in order to build some models from data. So the one key point for machine learning is their learning process, and also identify the goal and what type of data that we have, and what type of data are available, and what type of predictive information that we need to get from this model. So first, when we are identifying the data that we have, what data that are available, then we can discuss that if we can use some sort of supervised method or unsupervised method according to the availability of the data. And supervised method basically is a kind of learning process, using many options, many different learning algorithms based on the known input and target or output or labels that we know in the data at the beginning. But also with this information, we are able to do different problem type, different problem model that we can develop for classification, minor classification or regression type of models. And this type of model can provide some predictive information regarding with the health status of the machine or critical component, if it is okay or not okay, basically. Or sometimes some failure prediction, different failure types, different faults that we identify in the historical data. Then we are able to classify and do some fault prediction based on this information. And also with the regression type of analysis, we are also able to estimate the useful life left for a critical component of our machine or system that we are taking care. But in most of the case, and also in the industry, I think, this is what we really see. In most of the case, we need to take care with unsupervised approaches because we are having lack of labels, lack of failure histories, and so forth. And in most of the case, in industry, when we start collecting data, and we see that we could not have this full round to failure history in order to make a good prediction. So there are really lack of labels, lack of data in order to associate with some sort of important parameters that we are collecting from the machine. So we go with this unsupervised approach and basically try to understand and use some simple or sometimes some advanced clustering algorithms in order to identify and see and observe different patterns in the data, and then try to label these different patterns, cluster patterns, with this other type of information, contextual information. For example, we can check the maintenance logs, manufacturing execution system data, and some sort of other data sources. Or in most of the case, what we do, we discuss with the domain people from production and maintenance, and we try to basically understand, okay, we observe these patterns, so what does it mean basically in terms of machine point of view or other physical characteristics of the machine or component and so forth. So just before start this demonstration from the use cases, I would like to... Really? Okay, I'm so sorry. So I need to be very quick. So I will show these use cases from two different projects that I have collaborated with many industrial partners, manufacturing partners, of course in Sweden. And then these two projects, Summit and PACA project, have been funded by Vinnova, Production 2030 programs. And if you would like to get more details, I think you can click on this slide. So the first use case that we work with one of the manufacturing company, they are producing the motor engine, truck engine, and we actually selected two tooling machines or two bottleneck tooling machines in engine component line. After the discussion with the domain people from production and maintenance, then we decided to analyze vibration measurements for these critical tooling machines. And then we get the data from the IoT link sensors with the agents. These agents make the data under understandable formats and put our database management system. And then we also have the data from not only the external sensor, but also we have the data from the machines. And for data from the machine, that we are also able to know that which motor block has been produced when we have this measurement as well. We try to synchronize both data sets. And vibration measurements, basically, from these two different sensors with the 1 second resolution from spindle motor, and gearbox of the machine. And then we use the different features like acceleration and velocity measurements. And then we use the peak values. Acceleration peak is a time domain value, and we use also the velocity and acceleration root mean square value as well with the frequency domain. And then we synchronize this. We started and discussed with the companies, because this is a continuous measurement data from the sensors coming from. And then we need to find some sort of machine, when the machine is idle, basically the spindle is spinning up period without loading anything, without engage any product. Then this period was especially the interest by the companies to understand the health of the spindle. And then we actually design a full approach, including data pre-processing and feature extraction. Then after that, we fused these different features to using some algorithm, which is called principal component analysis, to create health indicators. And then we used these health indicators in order to build an anomaly detection model using the LSTM, long short-term memory autoencoder, in order to find basically the anomaly points in the data. And this approach is fully unsupervised approach without requiring any labeling in the data. And then we got to these results in the end. There are really promising health indicators for easily monitoring the performance of the machines over time cycles, because at the beginning, company people, domain people were quite unsure which parameters, which value is really important to follow. But basically, we fused all this important information in one health indicator for 2 machines, and then try to measure and easily visualize this. And then also we identified this LSTM model, identified these anomalies with that 99% validation accuracy. And then, as you see this on the figure, right bottom, we get to these anomaly points, it's illustrated with the red points on the figure as well. So this is quite important and useful diagnostic information for the company people, how to take care and to get the other data sources and understand what should be done based on these anomaly points. And another approach, should I continue or should I finish my presentation?
Yeah, if you could perhaps have a concluding
maybe yes, I
word
can.
And refer to the presentations that you have.
Okay, I'm so sorry. So I'm always very over-optimistic about the presentations, but there is also at least a slide I hope will be provided later on. So
yeah, they will be provided afterwards. Yeah.
I'm sorry for that. So conclusion in general, I think there are, of course, we observed that there are many lessons learned along the way. And one challenge is data challenges because of the data characteristic, data availability and quality. I think is most biggest challenge in this area, and also other process challenges regarding with how to handle the data, how to transfer, visualize, store, integrate, and a lot of pre-processing challenges that we had along the way. And also, I think there are also some management and technical infrastructure challenges as well, which are most of the time we have been discussing this security, privacy information sometimes, and also governance of the data, and some sort of how to transfer, how to share the data in a secure way, and also some inadequate IT infrastructure also we faced a lot. In order to handle this high-dimensional data set. And scalability and deployment is a big consideration also during this implementation. And also, I think shortage of skills and talent, I think this is also an important issue. So we try to build really some cross-functional team, including data scientists, maintenance experts, and some other industrial practitioners in order to, and IT people in order to get or to have this collaborative platform sharing knowledge with the people. So I think the success is here based on my experiences, having the right data available and framing the problem with the key person, with the domain people, that they need to be, I think, involved in this process from the beginning in order to really identify the problem, features, and everything. And also evaluating the prediction probably is very important if they really meet the business objectives, what we discussed with the companies at the beginning. And also very much important to get the full impact of PDM is important to get the actionable decisions, model deployment. But in order to do that, we need domain expertise powered AI and also effective data management using appropriate expertise and secure infrastructure to develop especially trustworthy predictive maintenance, because the results from the trustworthy predictive maintenance should be really clearly understandable by the decision makers, and people need to trust this AI solution in order to really deploy and run it in the production in the shop floor and in the real production environment. Thank you so much. These are some studies that published already, so publicly available. You can find it in the slide, and I am really thankful for your listening, and my partners, graduated master students, production area of advanced, and of course, Vinava for their research support. Thank you so much. Sorry.